So I'm just going to go over what a perceptron is in this video. So all a perceptron is basically, you can imagine it being the simplest neural network that you could wrap your mind around. So all that it is it's a neural network with a very simple activation function. And there's no hidden layers. And that's basically all you can think of a perceptron as, just being that. It's just a neural network that's with a very simple activation function. The heaviside function, if you're familiar with that, is the activation function. But if you're familiar with that, but it's not necessary to know the name of it as the heaviside function because it's pretty straightforward. So this is just a schematic of a simple perceptron with two outputs. And we'll call this W11, W21, W31, W41, W12, W22, W32, and W42. So the 4 is coming from there, and the 2 is coming from there. And all these are just weights. Then we'll have a bias here, B2, and a bias here, B1. And then whatever the answer is here, we're going to have output here and here. So all no hidden layers means is here in this blue area, there's no extra nodes. Like there's not a connection here in the middle that then goes from there to there. That doesn't happen. That's all that no hidden layers means. And at the end of the day, our output O1 says take the input I1, multiply this number by it, take the input I2, multiply this number by it, the weight, and so on, add those together, and then add a bias term, and then apply the activation function to it. So if our activation function is given by sigma, then this is whatever this number W11 is times the first input plus the second weight times the second input plus the third weight times the third input, and so on. And then plus the bias term that balances all of them out. Now in this case, your activation function sigma of x is very simple for a perceptron. It's just 1 if x is positive, and it's 0 if x is 0 or negative. So it basically just says if, and so that's what this B1 is basically doing. It allows you to shift it, if you want the right answer to be -1/2, then you shift your bias as like 3/4, because then -1/2 plus 3/4 is going to make this 1. And so that's what the bias term is really doing there. So I'll show an example of where a perceptron can actually solve a problem. So let's say you're given two classes of things, say cats and dogs, and let's say there's blue X's and red dots, and these belong to two different classes, and you're only given 2 data points here. And I want you to be able to, given some other input, be able to predict, so let's give more data here to make it more clear. So let's say that this is the real world, quote unquote. Here's all this data. Okay, and let's say you can actually only see these 2 points. then I will claim that the following perceptron can actually solve this classification problem to separate the two. So this is your x coordinate, is going to be your first input, and this will be your y coordinate, will be your second input. And so this one will be even simpler than the one we just drew. So there's only going to be one output. It's going to tell you, let's make this bigger. So this is, we have some weight. We don't know what that weight is yet, and we don't know what this weight is yet. And we don't know what this bias is either. So this is our output. And I'm going to assign 0 to be, so let's also say that this point right here is, let's call this 3/4 1/2, and let's call this one 1/4 3/4. Okay. It's not, might not pictorially look like that. It's close enough. Yeah. So I'm gonna assign 0 to be blue x's, and I'm gonna assign 1 to be red dots. And I'll claim that if I set, okay, so how I'm going to get this is basically, and why I chose these points, is if you look at the line y equals x, then if it's below that line, you're going to get blue x's. And if it's above that line, you're going to get red dots. So we want to encode this line, basically. So what we want is, given the x coordinate, we want okay, so let's look at it this way. If y minus x is less than or equal to 0, I want blue. And if y minus x is greater than 0, I want red. So what I want is, I want W2 to be equal to 1, and I want W1 to be equal to -1, because W1I1, and remember this is the x coordinate, plus W2I2, and that's the y coordinate, is equal to W1 I'm choosing as 1, as -1, so this is -x plus y, because I also chose W2 as 1. This is y minus x. Now, if I choose a bias of 0, that means that sigma of W1, so this is precisely what I want, right? I just want the line y minus x. If I really wanted the line y minus x plus c, then I'd choose the B1 to be c. So this is W1I1 plus W2I2 plus B1 is equal to sigma of I2 minus I1 which is really sigma of y minus x, because I2 is y and I1 is x. And so this is equal to, recalling this function, this is equal to 1 if y minus x is positive, and it's equal to 0 if y minus x is less than or equal to 0. So that tells me that I wanted this 1 to correspond to red dots. So that tells me that I am red if above line y equals x, and I am blue if below line y equals x. And that is precisely what that picture shows us. So that's just a little toy example of how a perceptron works. So a good exercise to go through to, I guess, hammer this concept home is, if I were to give you, let's say, let's say this is 1, and this is the line y equals 2x plus 1. And now I have my red dots here. Well, actually, let's flip it. Let's put the red dots below it this time. So this is my data, and let's give you this point, and let's have this be 1, 2, and let's choose a blue X right here. This is 1, 4. And all these X's are here. And your goal is to build a perceptron that separates the red dots and blue X's. So it's a similar process here, but this is good practice with a different line here.